Okay. Yeah, hi Karthik. I'm audible?
Yes, yes.
Okay, so let's start. Okay, so let's start with let's continue our discussion on the gradient descent. Okay, let's have a quick recap of what we learned yesterday. So to start with, we understood the basic issue, the basic problem we are trying to solve over here is um, we have a loss function and we need to find out the minimum we need to reach at the minimum value of the loss function, correct? And there are
Yes.
2 points in our hand. One is m and b. Okay, we'll start with some random values of m and b, and from there we want to reach the minimum point. That is our problem statement. For that, we have seen the gradient descent is that algorithm, which will help exactly as per our requirement, right? So it is trying to optimize our algorithm by iteratively changing the parameter so that it will find out the lowest value of the function. And also we have seen that slope is one thing which will tell us in which direction we want to move. Okay, so whether you are on the positive side, if you the slope is positive, we would be moving in the I would say in this graph, we will be moving to the left side, or in generally, if the slope is positive, we will decrease the value of b such that it will try to move in the direction of the what
Left,
lowest
left.
loss. Okay, and if the
Yes.
slope is negative, we will move to the right, or we'll increase the value of b. Okay, so and also we have seen anywhere you start, so right, so after few iterations, it will try to converge to the minimum value. That is one point. And but later we have seen this is fine, the direction is fine, but we are having problem with the speed because the speed is more, even though direction is fast. Even if we reach the goal, we don't know that we have reached the goal, we will surpass the goal. So that's why we put a restriction on the speed using what? Using
Really, like learning
learning
rate.
rate, right? Learning rate. So we are using the speed learning rate usually. We will see. I'll discuss more on learning rate. Okay. So with that, we achieve two things. One is speed, also direction. So we are taking small steps so that we don't surpass the uh, what we say minima. So let me call this as minima. Okay. So that point. So that we have seen yesterday. So today we'll continue the discussion. So one thing I would like to start with is the effect of learning rate on gradient descent. Okay. So yesterday we have seen, right? So let's say this is our data point. Okay. So I was also showing you this one, right? So starting with random values, slowly it is trying to become the best fit line. Fine. In this process, its value of m and c are continuously changing. Fine. So now we are controlling the movement of this line with learning rate. Okay. So now what if learning rate is too slow? What if it is too high? Okay, so we will see that. So for example, so yesterday I think I said 0.01. Okay, sorry, it should be 0.1 actually. Okay, so this is mistake, so 0.01. So I can show you here. So if it is, let's say if it is 0.1, which is ideal. Okay, so what happens is it is starting, okay, it is starting from this line. Okay, slowly it is moving towards here and it is stopping over here. Okay, it is stopping over here, the line, that thick line. But if it is
Yes.
less than 0.1, this one, which is like 0.02, so it takes forever to reach this point. It will never converge itself. Okay, so the moment is too slow, right? So it will take a lot of time or it will not become the best fit line itself. Okay, because the moment is too slow. So we are
Okay.
taking very small steps. Okay. So, but
Okay.
if
Okay.
given sufficient time, obviously it will reach logically, right? So, for example, I need to cover 10 kilometers distance. Okay. So, if I am taking, okay, a step of like 100 meters, so I will reach in some time. But if I'm taking like 0.0001 meter, okay, per day, okay, in one day I'm taking only 0.001 meter. That means it will take few years to cover 1 meter and so many years to cover 1 kilometer and even so many years to cover 10 kilometers. Okay, so that means logically, mathematically, you can say that if you give like some thousands of years, obviously I will cover with this speed like 0.001 meter per day. I can cover 100 kilometers. Okay, but practically it is impossible solution, right? Who will wait for such times, right? So similarly, the same concept here, like if your learning rate is too slow, like it will almost, we can say that it will not converge the solution, converge to solution. Okay.
Yes.
And if your speed is if your learning rate is high, okay, so then it will surpass the solution. So it is starting from here, it will reach here, and it will come here, and it doesn't, and it will just move away. Okay, so learning rate is I would say one of the important parameter. Fine. So with that, so usually it will be like 0.1. Okay, so 0.1, but you can, these values you don't take it for granted. Okay, it will depend on the data set, how long, how big your data set, and what is the nature of your data set. So we can experiment. So it is best practice to start with 0.1. Okay, and see the time and the loss, the best fit line loss, how much you are getting, and then you can experiment with small values, like you can range from 0.2 to 0.3. Okay, and see which is giving better results. Okay, so but that is overall effect of learning rate on the gradient descent. Okay, so but the main concept is same. Every time you are changing the values of NB, you are getting new line and new loss and then new MNB, and keep on changing, finally reaching the solution. Okay, that is one thing. So now in our yesterday's discussion before closing, so we discussed about few things, right? So regarding this point, so over here, so now when we say the loss function, okay, so see, as of now we assumed the loss function is this. Okay, so why we have assumed this? Because initially the loss, if you're far away, it will be high, and slowly as you move it will be low, and then again if you move away it will be high. This is fine, this is for a simple data set. Okay, and for 2D, okay, mostly if you are working on 2D it might be this, but if you increase the number of features like 3D 4D, okay, in 3D 4D plane, the loss function may not be always this. Okay, there might be, because if the data is in multi-dimensional, as I said, each feature is considered as one dimensional in machine learning, right? So if you have three dimensional data, okay, that means if you want to predict some score is, for example, predicting house price is my output variable, since we're discussing linear regression. So there are three features. One is number of bedrooms, second is like size of the area size of the house, and third thing is, let's say, facing of the house. Okay, there are three features, so it is three-dimensional data. Okay, so in that case there is possibility that you know the loss function might be something like this also. Okay, so over here what is happening is there are multiple minima. What is minima? Minima is that point where you can see a minimum loss. Okay, so over here also there is a minimum loss. This is also minimum loss when compared to these points. Okay, but when compared to these points, this is not minimum. Okay, similarly this is also minima when compared to these points. Okay, but when compared to this is not, and when compared to this is not. Okay, so that's the reason I said, so this is the lowest minima is called global minimum. Okay, and these two are called as
Okay.
local minimum.
Local.
Fine. So now, if you think about it, the first step, what we're doing in gradient descent, we are starting with some random values of M and B. Okay, because I don't know where to start. Okay, so somewhere I need to start. Same thing over here also. If you see now, see, it is starting somewhere. Okay, the line started from somewhere. So if it is starting somewhere, that means it is having some value of M and B, right? It is some random value, so it's called random initialization. Okay, so the way how it is getting randomly initialized is also having effect on whether it is reaching the global minima or local minima. Agree? Because if it is starting here, right, so obviously it will calculate the slope. Okay, it will calculate the slope, and when you calculate the slope it will be negative, so you will increase the value of B, then it will move in this direction, over here this direction, over here this direction, and it will reach here, and it will try to go here, then it will, the slope is positive, and it will reach here. Okay, then it will do some oscillations over here, and finally it will settle here. Agree?
Yes.
If it is initializing here, one. Same thing if it is initializing here also works, because if it is initializing here, so it knows that if I move up, okay, if I move up, I'm moving away from this minimum point. Okay, it doesn't know whether it is local or global. Okay, try to understand it, it doesn't know, we are just experimenting. Okay, so if you already know how does a loss function looks like, then you can know. But when the line is changing itself, it doesn't know how many minima or how many maxima. It doesn't know. The only thing it knows is which direction I should move. That's all. Calculate the slope, determine the direction I should move. That's the only thing it does. And the direction speed we are controlling with learning rate. That's it. So if it is starting here, so it will calculate the slope over here, and the slope will be positive, so it will move here. Okay, it will decrease the b, decrease the b, decrease the b. It does this. That's fine. But the problem will come when you start from here. When you start with the point 3, okay, so what will happen? So it doesn't know that there is a global minimum over here. So the only, as I said, what it will do, it will calculate the slope. So now slope will be negative, right? When slope is negative, obviously it should move this way. Correct? It will move this way and it will settle here. It will come here, again it will move here, finally it will settle here. Agree? So, and when it is settled
Yes,
here,
Pankaj.
obviously it will not come out of this because it has no idea that there is some other place where the loss is even more lower than this local minimum. Okay? It will just think, I have, based upon the scenarios I have seen, so this is the minima. So it doesn't know information outside this. So it will settle over here, thinking that this is the global minimum. Agree? Same thing happens if you start from here or here. It will settle here only.
Yes,
But
yes.
but we know that there could be some more, some other place where we can find out the least minimum value, which could be the global minimum. Okay. So, but now if you think about it, what is causing the problem? Can you tell me what is actually causing the problem here?
Multiple minimas, because of that, it's
No,
unable
no,
to understand
no, no,
where
no.
to,
See, multiple minimas are there because our loss function is like that. We don't.
because it doesn't know the
Correct.
direction where to settle and in which direction direction. Yeah, mainly direction only. It doesn't know.
Huh, correct, correct. But the problem is the way how we are initializing, right? So if we are
Where exactly we
initializing,
have to start? Where exactly?
correct,
Should be. Yeah,
correct. So where it's called initialization, okay? So where
okay.
we are starting, okay? If that is, if we are lucky, we are reaching here, okay? So
Correct.
every time we cannot be lucky, right? So to do
True.
that, to handle this problem, right? So and
Hmm.
we have few types of gradient descents, okay, that we are going to see. But before that, as I have said, we have seen local, global, okay, and there is also something called a saddle point, okay. So the
Okay.
saddle point is nothing but, so for example, you are having a loss function like this, okay, but let's say the loss function is like this, okay. That means you are having this function, and after that there is kind of plateau, okay. It's like flat for some time,
Yes.
fine. So now the problem with this is if you're starting over here, okay, if you're starting over here, so it will, so the what is the goal, what is the driving force of this gradient descent? It always tries to move in that direction, which will give lesser and lesser loss. Okay, the loss should be less. Agree? That's why if you're starting here, it is coming here in the second iteration. Why it is coming here? Because the loss over here is less than this. Next, it is coming here. Next, it is coming here. Agree? But if you start here, for example, random initialization happened here. Next, what it does, for example, it has after one update, it went here. Okay. So, but the loss between this point and this point is almost same
True.
because it's flat. Okay.
Flatline. Yes.
Only if you have steep, then the loss is changing, either
Yes.
increasing or decreasing. But if it is flat, what? The loss is almost same. So it gets
Yes.
confused. So, so there is no reason for it to update the values. Agree? Because the loss is almost same. So if you see uh, M new equal to M old minus learning rate of slope, okay, into slope. Fine. So now if slope is almost same, okay, so then M new will be M old, correct? If slope is getting different, so you are changing this value. But if slope is every time the same and learning rate is fixed, so m new will be equal to m old. That means my new value of n is equal to my old value of m. That means what? The gradient descent algorithm is not updating anything. Correct? If my old value
Yes.
is same as new
Yes.
value, that means what? It is, I'm
Yes.
not moving.
Correct.
Okay. So
Yes.
but the point is, but tricky point is this particular point is neither a local minima nor a global minima, but still we are getting stuck.
Yes. Yes.
Clear? At least
Clear.
this is if you are getting stuck here, that is not
Mm.
best, but at least it is local minima, if not global.
Minimum. Yes.
Okay.
Yes.
If
Yes.
you're stuck in here, that is the perfect solution because that is global minima. Okay.
Correct.
But here with the model is not settling here, but it doesn't have the motivation, I would say, to move forward, because the whole point of gradient descent is it will move forward. Okay, only when it sees that if I move in this direction, my loss is decreasing. Only then it
Correct.
will try to move forward. Okay, but here,
Correct.
for some points over here, okay, it will start. It is starting here. If it comes here, okay, the loss is almost same. So which direction it should move? Correct? Because if I'm here, I will move in this direction. Next, in this direction, constantly I'm seeing some change, some improvement. Okay, I'm happy. But if I'm here, if I move this point, okay, even I'm at this point or this point, the loss is same. You see, loss is same. So which direction I should move? I don't know, because it doesn't have the information that if I move a bit forward, I'm having minima, I'm having one more minima, I'm having one more minima. It doesn't have that information. It is randomly experimenting. It is only caring about my this update versus my previous update. That's it. Only based upon previous update, I'm updating this update. Correct? That's what the whole equation is. My n new is dependent only on my old new. Apart from this, it doesn't know anything. If my old new is worst, then I'm going to new m new. If it is still worse, I'm moving again. But if my old new is almost same as m new, that means same value. My values are same. That means slope is same. I'm not changing anywhere. Then you are getting stuck over here.
True.
You understood?
Yes. Yes.
Right? So this particular point is called as saddle point.
Okay.
Okay? It's called as,
The point where it starts
yeah.
at both new and new one and old one. It's same.
Yeah.
Yeah.
No, so where it's stuck is no, not where it's stuck. Where it's stuck is correct, but more importantly, it is stuck, but it is neither a global minima nor a local minima. That is the main point. Because here also it will
Okay.
get stuck. Here also it will get stuck. Here also it will get stuck. But this is fine. Here it is getting stuck, but it is not a minima at all. That is the problem.
Mm-hmm. Okay.
Okay. So if I just show you saddle point, yeah, it will be like this. Okay, so if you see in this 3D, so it's like almost flat. Okay, this is curve,
Mm-hmm.
but for some reason it is in the update, it becomes like a small plateau. Okay, the update is
Okay.
all not much. Okay, so
Okay.
that point
Okay.
is called saddle point, and the reason why it's called saddle point is, the horse saddle. Okay, so
Yes. Yes. Yes.
see this shape and horse saddle, so it is almost, you see this part, this
Yes.
shape.
Yes. Yes.
Okay, so it is similar to that, so that's why it's called saddle point. Okay, but that's the point. So main point is we have three things. One is local minimum, global minimum, saddle point. Global is the most lowest one. Locals, there could be
Mm-hmm.
many locals. Okay, but global will be only one. And saddle point is
Mm-hmm.
which is neither local minimum nor global minimum, but still the point is getting stuck. Okay, that's
Okay.
one point.
Okay.
Now going ahead, now that is one point. Now coming back, our main aim is like it is getting stuck in the local minimum. Okay, so now to solve this, basically we have, okay, not to solve this, but just speaking about gradient descent, we have three types of gradient descent, Karthik. Okay, one is batch gradient descent, one is stochastic gradient descent, okay, and one is mini batch gradient descent. Okay, so one is batch, one is stochastic, one is mini batch. Okay, and the three of them are very easy to understand because there is only one thing that is different from these three. Okay, but obviously one of these is very helpful, and each of them have their own advantages and disadvantages, and we are going to see that. Okay, so we'll just try to understand. what is batch, stochastic, mini batch. So as the major difference between this is see the process is same. All these three are gradient descents. That means the process is same. Taking a value, random value, updating the parameters, repeating the process is same. Okay, but there is only one fundamental difference that is creating three types is how many number of rows you are considering. Okay, that will decide whether that is a batch or stochastic or mini batch. Okay, so don't worry, I will just quickly see what is the difference. Okay, so in batch, right? Sorry. Okay, so when you're seeing batch, the name itself says that you will pass whole data to update parameters. Okay, so what does that mean? So it is very simple. Okay, so if you see here, what is happening in the gradient descent, we are doing this. Okay, so even if you take M or B, fundamentally what is happening, okay, fundamentally this is happening like M new equal to M old minus learning rate of slope. Okay, and slope, how you are getting, we are doing dou L by dou M. Okay, derivative of loss with respect to M. Okay,
Yes.
now this M is what? M at the previous point. Okay, wherever the previous M old, okay, you can say M old. Okay, wherever I want to calculate the loss. Okay, see, just like this, if I go here, yeah, so if I'm at this point, this is my M old. Okay, now from this M old I should go to M new. So what I will do, I already have M old, I will put it here, minus learning rate 0.1. Now slope is what? Slope is dou or dl by dm. So we have the loss function, take that loss function, do derivative with respect to M. Okay, and you will get some value. Okay, over there you put the value of this M naught. Okay, you put the value of this M naught. Okay, so if you, for example, I will just show you quickly how does this derivatives looks like. Okay, for example, you have L equal to, what is my loss? Okay, loss is summation of y actual minus y predicted whole square. Agree? Okay, I'm just deriving. So my this will be summation of yi. Okay, minus what would be, what is, from where you are going to get the prediction? I'm going to get the prediction from my best fit line. And what is the equation of line? Mx plus b. Okay,
Yes.
so replace this y hat with mx plus b, it will be minus mx I minus b
Minus.
whole square. Okay, so now when I'm saying this slope, if you are worrying like how I'm going to get this dou L by dou M, so just it is simple. So this is my L. So if I want to do it with respect to M or B, okay, so if I do it with B, dou L by dou B equal to what? I need to differentiate this. So it will be minus 2, sorry. Okay, it will be minus 2. You will do come here and summation of yi minus mxi minus b. Okay, and yes, so internally it will be when you are doing with 0. Uh, Yeah. So yeah, dou by dou minus 2 into summation of y minus mx plus b. And if you are starting with some random values of b equal to 0, okay, you need to put the value of b over here. Similarly, if you do dou L by dou m, so it will be minus 2 into summation of yi minus m xi minus b into, internally again you need to do these derivatives, right? So this will be 0 and this will be xi. Okay, so it will be xi and this will be 0. Okay, so And now if you put initializing value of m equal to 1, then you need to put the value of 1 over here. Okay, m value will be 1. So now these are the values of dou L by dou B and dou L by dou M. Okay, so now when I'm saying mn equal to m naught minus eta into dou L by dou M. Okay, so I mean this. So
Okay.
wherever yeah. So over here, if you want to move from m old to m new, so you will put this mn here minus m naught value here in slope. So for slope, you already have the equation. So you if you want to
Good.
calculate dou L by dou M, take this equation. Okay,
Okay.
and you are going to, you already know yi actual values, xi actual values, but m is what? M is my m old. My m old is whatever the value you are having m old. Put that m old here. B you will get it from similarly b new equal to whatever the values you are having, right? So from there you will pick it up, and xi is the
Okay,
actual
actual.
values. Okay, so this is what I mean. So but now point here is that is fine, but what is batch is you will pass the whole data to update parameters. That means to calculate this mn, to this is everything is same. So this part mainly focus on this part. This dou L by dou M, right? We're calculating the loss. Okay. Now loss is what? Actual value minus predicted value, or predicted value minus actual value. That is loss simply. Okay. So no loss, you can calculate it for any points, right? If I pass only one row, okay, if you have the model, you pass the only one row, the model will give you prediction. You have the actual value. Predicted value minus actual value is the loss. Agree?
Correct. Yes.
If you pass two rows, you will get two values. That is loss of two, set of two. 10 rows, set of 10. Right? So you can calculate loss
Correct.
for any set of data values. That is the only difference between these three. If you understand this, that nothing more. So in batch, what happens is you pass the whole data. That means to calculate this loss, you pass all the data. That means if you're having the data set is having, let's say 10K records.
All 10K records we need to
Yeah.
pass. For each and every record, it will
Correct.
give some loss or whatever.
Correct. Okay. So that means for 10, if you see this equation, dou L by dou M, so yi, xi you have, right? So you are doing the summation,
Mm.
right? So
Yeah.
for every time you are going to pass the actual value, okay, and its corresponding m value, right? M is what? My m old. Okay, so when you're starting with some random value, right, you're starting with some random value, m old will be that m value, and you are doing you are having the sorry, okay, or I will just write it over here. Wait to take the attention. Okay, so I'm just putting here, so my dou L by dou M will be equal to, I have this minus 2 summation of yi minus m xi minus b into xi. Okay. Now say slope m, initially we have started with some m old equal to 1. Okay, example, you can take, usually we take small values, but you can take any value as insulation. So now point here is when you are doing this one, okay, so for this loss, if you consider all the complete data set, okay, take complete data set, calculate the loss of each and every point, okay, and then if you do this, okay, that means what? For each and every data set, if you do this, okay, then whatever the value you are going to get and you are updating it, right? So then that will be called as batch gradient descent. Okay, because you consider the whole batch. That is simple thing. Okay, you consider the whole batch, you calculate the loss of, you calculate the loss of the complete data set. Okay, and you did this part. Okay, dou L by dou M by 0. This is you are doing it for complete data set. Okay, this it summation is there, right? So you are iterating it for the complete data set. Okay, that first row you are taking the actual value, you are putting an m equal to 1. This m naught will be 1, and xi minus b into whatever the values of okay, values of xi, the actual value. You put this, you do this. Okay, you run this summation for like all the data set, 10,000 rows. You will get some value.
And So M value is the same for for all
Correct, correct,
records, for all
correct,
content data set.
correct. Because we don't know another M value. The reason why we are doing all
True.
this is to find out this new M value.
Correct.
Okay. So you are starting with from M0. I need to go to
Mm-hmm.
Mn. Okay. To do one step, for one step, if I need to move, what happens is you will pass the complete data set. Okay. And then you
Yeah.
calculate the complete loss and then you will put it over here. Once you do this, you will get this dou L by dou M, you will get this. And then you will put this M naught will be 1 minus
Mm-hmm.
learning rate is 0.1, for example, into whatever
Yeah.
you are going to get. Let's say, as an example, 10. I don't know, just 10.
And
Whatever the
that,
value you are
yeah.
going to get, that is M naught, M new.
New point, new one. Yeah.
Okay. So that is just what is, batch gradient descent. Fine. So it will consider the complete, sorry, it will consider the complete data set.
Yeah. So again, we need to repeat the same thing using another new M value
Correct,
for that.
exactly. Correct. So usually what we do this is we call this as epochs. Okay. So epochs is
Okay.
nothing but how many times you are training the data. Okay. So in deep
Mm-hmm.
learning, they use this word. Okay. It is nothing. It's called epoch. That means how many times you are training on this data set. Okay. So
Okay.
usually if we have like 10 epochs, that means what?
Mm-hmm.
First time in epoch 1, E1, take full
Mm-hmm.
data set, update. Now
Okay.
take E2, take full data set and update.
Okay.
E3, take full data set, update. Like that, 10 times it will update. Okay. From M0 to M old to M
M10.
new to new,
Mm-hmm.
new to new 3, new
Mm.
2, like that. 10 times it will update.
So we will get two, I mean, 10 M values, new,
10 M
like
values.
M not to
Correct.
M10. Yeah.
Correct. But we don't care about that. We only care about the latest one, right?
Yes. Yes. Yes.
Okay. Because it should be better. The whole point is the last one should be, the current one should be better than the last one. It should be better than again the last one. So 10th one, ninth one, okay, first one, second one, third one. Okay. So that's what. So initially, when you're doing epoch one, it will be random values of, okay, I will just say M random, B random.
Okay.
From this, it will go to, let's say, M1, B1, M2, B2.
Mm-hmm.
Okay. So from where you're getting B also same formula. Okay. I'm
Yeah.
not writing the formula, but for B
Yeah.
also,
Yeah. Got it. Got it.
same thing.
Got it.
So for B, it will use, uh, it will use this one. Okay. For B. And it will update the values. Okay. So like that, the main concept is we understood the gradient descent, but try to understand what is the difference in batch. Batch is simple. So if you take complete data set, calculate the loss for all the data set, get the value, and then update the values. Okay. Clear?
Yeah. I have another doubt.
Yeah.
Just for example, I mean, just now you said whatever the recent one, that is the best one. That's what you said, right? But
Correct.
in the gradient descent, if you see that graph, based on learning speed, for example, if speed is more, it's going, I mean, it's going our actual, I mean, passing the point. Okay. So again, we are changing the speed based on that. Okay. And the direction as well. Okay. It passes our actual goal point. So it's going, after that, again, we are changing the speed and changing the direction based on that.
Correct.
So, based on that statement, how will get to know that recent M10 is the best one? Maybe M8 is also best because speed might change for M9. It passes that actual minimum point, low point.
Correct.
Did
I
you
got
get
your
my
point.
point?
I got your point. So yeah, exactly. That is the thing which we need to check and find out. I mean, see, I got. So you are saying that over here. So it is not stopping here. So it is moving. Okay.
It go to that minima. I mean, the minima which you have
Yeah.
shown.
Yeah. It
Map.
is going here. So how can I say that this is better than the previous? So, but here, if you see, the loss is again increasing, right?
Yes.
First thing is, see, two things. We need to fix, okay, one by one. One is like how many epochs you need to run is one thing. And second thing is what is the learning rate. Okay. So initially, if you take learning rate and okay, you try to tune it. So first you can decide on what is the best learning rate. Because if you run it for like, let's say 0.5 in this case, you can, and if you plot a graph, so how does the graph look like? Initially, the graph will be high. Okay. High.
Mhm.
Okay. Then slowly it is decreasing because as the line is moving here, okay, if it is here the line is here, but after that again if you keep on moving, okay, so the graph is again moving up, the
Wow.
increasing and
Yeah,
again
yeah, yeah.
constantly increasing.
Got it, got it. So for every batch, we need to calculate the error,
No,
minimum error.
no, no. Learning rate will be fixed. Okay.
Yeah,
Learning rate is, for example, learning rate is 0.1. Okay. If you find out
yeah,
learning rate 0.1 is giving good results. Okay.
testing. Yeah,
Let's say
okay.
you run for one epoch. Okay. You run on only
Yeah,
one epoch and you
yeah.
experimented with like learning rates. Okay. If 0.1 is giving best results, you will fix that. And after that, okay. And after that, if you are passing this batch gradient descent, okay. So
Mm-hmm,
it will start with here. Okay.
mm-hmm.
And every time it is moving towards this, towards this, towards this.
Correct, correct, correct.
And once it
The
is
same.
reaching the best fit line, okay, and it
Mm-hmm.
will not go over here because if it is going over here, because the learning rate is so small,
Got it,
so if it is
got it,
over
got it.
here, it will again come back. It will
Okay,
do
okay.
oscillation, right? It will just come back.
Yeah,
But if
so
your
it's, yeah, yeah, yeah.
learning
It's
rate is
everything
high,
part of algorithm, right? Yeah, yeah. Got it.
okay, so
Yeah.
that is regarding the batch gradient descent, okay. So and the goal is every time you move to next value, it will be better than the previous value. Okay,
Okay.
because we are considering the whole data set. Okay,
Correct.
you're taking the whole data set, finding, and then you are moving. Okay, taking the whole data set, finding, and you are moving towards the direction. Okay, that's fine.
Okay. Okay.
Now, if you see coming to stochastic, we have another thing called as stochastic. Okay, so first I
Mm-hmm.
will tell you why we should learn stochastic because this is fine. Okay,
Mm-hmm.
so so if you are, but the problem with this batch is, let's say you are having 1 million records.
True. Optimization thing.
Correct. So million records, as if you use batch, what happens? You need to take each of this
Yeah,
record,
it will
calculate
take
the
some
loss,
time for, yeah, yeah, yeah.
okay, and then you need to update the values. Again, if you are trying 10 epochs, so
Mm.
10 into million, 10 million, okay, okay, time, not 10 million actually. That means it will consider in every epoch all the data points.
Correct.
So loss calculation is you need to calculate the loss for all these minimum million points and it will
Yes,
update one.
yes, yes.
Okay. Then again, second epoch. Okay. Second time when you are passing, again it will consider all the data points, calculate the loss of all the million points and then update two. Okay. That means it is so much time consuming, resource consuming, right?
True.
So, and in practical, you
And
will
we are not,
have,
and we are not sure about how many epochs it will take because
correct, correct,
might be take any number of. We don't know, right?
right.
When we will get
When it
the
will converge.
best. Yeah, yeah.
Okay. So, and this is only for 1 million, but in practical case, right? So you will have millions of records. Okay.
True.
So it will take forever and millions of records and that too multiple features. So for example, if you have 10 million records
Mm-hmm.
and okay, some 15 features, okay, which
Oh,
is not
oh,
rare, which is very possible. Okay.
okay.
So it will take forever if you use batch gradient descent. Okay. So the reason, because every time, okay, what works in practical world is like which is fast and which gives better results. Okay. If not the best results, even if you get better results, that is fine
Yeah.
because you're saving time. Okay.
True.
That means like this is an example. If a company is saying, if you give me 10 years, I will double the, okay, revenue, or in 2 years, I will give you 80% of the revenue. So I'll go for 2 years because in 2 years, I'm going 80%. Instead of waiting 10
True.
years, for doubling, right? Similar example. So did I discuss random search CV and grid search CV?
No.
In previous classes, like when we were having sessions earlier, did we discuss random search, grid search during
Mm-hmm.
train test split? We did not discuss. Okay, fine. Okay, so there also we'll have similar concept. Okay, anyway, coming back. So in stochastic, what we do is very simple. Okay, so here, funnily, what we do is we'll take randomly one row, only
Okay.
one row. Okay, so that the meaning of stochastic is random. Okay, randomness. Okay, so
Okay.
here randomly we take one row and with only one row we calculate the loss. Okay, we calculate the loss and then we update.
Okay.
That we do, that we do as many number of times. Okay, as the number of rows. Okay, so that means what? That means what? If you see, there is small tricky thing. Okay, so over here. Okay, just give me 1 second. Okay, so over here, yeah, as I said, there is a small tricky thing over here we need to understand. Okay, people usually might get confused here. Okay, so see, if you are having, just, oh, sorry, sorry. Okay, yeah. So try to understand carefully. You are having, let's say, 5 epochs. Okay, hello.
Yes, five
Okay, yeah.
box.
Okay, you are having 5 epochs. That means what? 5 times and passing the data set. Okay,
Mm-hmm.
in each epoch, earlier what happened? In each epoch, we consider the whole data set, calculate the loss. But here, interestingly, what happens is in each epoch, okay, we will take only one point at a time. Okay, we'll get one point at a time, check the loss, and update update the
One
parameters.
value.
Okay, and we
Yeah.
will do this n number of times. N is
Mm-hmm.
number of rows. Okay, so if my rows, number of rows, n equal to number of rows,
Okay.
number of rows. So in each epoch, in epoch one, what I do is I take
Randomly pop one
n
record.
random n times. Okay, n times random values I take. Okay, and every time I calculate loss and I'll update the parameters. Okay, so if I'm having 5 epochs, okay, 5 epochs.
Five
So
random thing.
5 times I do, and inside each time I am going to update it n times, 5n times. Try to understand carefully. See, in each epoch, it will update n times. Okay, for example, my number of rows are 100. Okay, just if you take
Mhm.
some number, it will be easy. Okay, 100 rows are there.
Mhm.
Simply 100 rows. My
Okay.
data set is having 100 rows. Okay,
Okay.
so just
Mm-hmm.
consider one epoch. Okay, in one epoch,
Okay.
it
Okay.
will update 100 times.
One epoch.
Okay,
Okay.
okay, only one time
Mm-hmm.
I'm passing. Okay, forget about epochs if it's confusing. Okay, forget about epochs. Okay, one only I have complete data set and I'm asking stochastic gradient descent to apply on this. Okay, so what it will do? It will take 100 rows. Okay, but it will not consider all the rows at a time.
Only one at a time.
Only one randomly it will pick one row, calculate the
Yeah.
loss. Okay,
Mm-hmm.
and update the values. Okay,
Okay.
calculate the
Mm-hmm.
loss only for one row, one single row,
Okay. Yeah.
and
Yeah.
update the values. You got
Mm-hmm.
m new.
Yeah. True.
Done.
We got it.
Second time
Mm.
again take another random value, calculate the loss, update the
Mm.
value.
Okay. 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 Okay.
Third
Got
time
it.
some other random value, update. Like that, how many times it will
Mm.
do?
100 times.
Because 100 rows,
Mm-hmm.
100 rows are there. Okay, so that means what?
Mm-hmm.
In one epoch only, each epoch it is updating n times.
Yeah.
Okay, it is updating n times, where n is the number of rows. Okay,
Okay. Mm-hmm.
that's what. So if you're having 5 epochs, that's why I said 5 into n times. Okay, that means if your n is 100, 500 times it is updating.
Okay.
Okay, 5 epochs 500 times. But here if you see, in 5 epochs, how many times it will update? For example, over here in batch. Okay, in batch, if it is epochs equal to 5, how many times it will update? Can you tell me?
Oh, updating, right?
Right,
So 5 times only.
exact, perfect, only 5 times. Okay, the difference should be simple. Take all data set it will take every time update, or again take complete data set update, complete data set update. Like that 5 times it will do. But coming here, as I said, in each epoch only it will do 100 times.
Hmm.
Okay, updating is 100 times. Try to understand. Calculating
Yeah.
loss
Yeah.
is
Got
also
it. Got
100 times here. But here, if you see here, if number of rows is 100, okay. So here in epoch 1, in batch, what will happen in batch? In epoch 1, it will calculate, it will, because it is using all 100 rows, okay. That means 100 loss it will calculate. Okay,
Hmm.
100 loss it will calculate, but combinedly it will calculate. Okay, it is considering
Yeah.
all 100 values at a time, calculate the cumulative loss, and then update only once in one epoch.
Correct. Correct. Correct.
Second time, just take again all 100, update again, update again, like that only 5 times. That's it. So you are getting only 5 new values of m.
Well,
Clear? But here in one epoch only 100 times it is updating. Update and 100 times it is updating. Okay, because it is updating for every value. Simple. Okay. So 5 epochs, 500 times it is updating. Clear?
clear, but
Yeah, let me complete. Let me
uh,
complete. Once I
yeah,
complete,
sure, sure.
then I think some of your doubts will automatically get clarified. Okay. So now, why this is? Okay. So when I also heard it first time, so with one row or one row, how it is helpful. Okay. The interesting point here is the stochastic nature. Okay. So stochastic nature is random nature. It's a randomness. Okay. English word is randomness, meaning. Okay. The usefulness is, if you see the main reason in the starting of the session, I told you, if you're having a loss function like this, okay, if you're having a loss function like this, okay, and it is called just give me 1 second. So it's called concave. I think it is called concave. Yeah, so this is convex. Okay, usually it's called convex. Okay, if it is convex, that means you are having only one minima. Okay, this is non-convex. Okay, you are having multiple minima. Okay. Okay, so if you this is concave convex, only one minima. Getting only one minima.
Yeah.
If it is non-convex, you can have multiple minima. So this will become global minima. This is local minima. Okay. So initially, I told that if you're having a convex, it's fine. No need of any other methods. Directly start anywhere. You will obviously reach here. That's cool. Okay. Convex. But the problem comes when you are having non-convex. As I said. Okay. This is non-convex. So over here, the problem here is, see, here you will understand the advantage of this batch and stochastic. So over here, if you're starting using the batch, you started here. See, Karthik, you started here with batch. Okay. So now what we're doing, randomly you started here. So then you took the complete data set, you calculated the loss. Then you got new point. Then you moved this side. Okay. Over here, again you took the complete data set, you moved here. Again, you took the complete data set, you moved here. You are reaching here, that's fine. But the problem is, even if you are here, what will happen? You are taking the complete data set and calculating the loss, and you will move this side, okay, which might make you settle here in the batch. Okay, but in stochastic, what is happening, randomly it is picking values. So for example, initial random value is over here. Okay, randomly, for example, as I said, if you're having 100 rows, how many times it will update in one epoch?
100 times.
100 times. So first time, randomly it is taking some value. Okay, let's say that is this value. Okay, it will move this side. Okay, but after that second time, randomly, if you take another point, that point might be here. Okay, second time, when it is taking some other random value, okay, if it is taking some random value, okay, so it might be some other data point, right? So it is not considering complete data point. Okay, then the loss will be very different for that data point. Okay, so then the loss might be over here. Okay, but third time the loss might be again here. Okay, so the reason is, don't get confused, the reason is there is high probability that it will come out of this local
Come
minimum.
out of that loop. Yeah, yeah, got it.
Okay, that is the main point I'm trying to convey. Okay, but
Got it.
with batch you will, if you start here, definitely, because every time you're taking complete data set, you will stuck here. But because
Yeah.
of stochastic randomness, even if it is coming over here, but randomly, if you take some other point, it might go here.
Yes.
Okay. because of the loss. Okay, again it might go here. Okay, it might go here, it might go here. Okay, but there are high chances that it will come out of the local minimum.
Okay.
Okay, it will not get stuck over here. Okay, because if you take new point, okay, point one, there is some loss one. Okay, so it is over here. But second time it is not taking all the data set, so some random point it is taking p2. Okay, it is calculating new loss. Okay, that new loss might be over here. Okay, third time it could be here, fourth time it could be here. But the problem is there will be fluctuations. Okay, there will be fluctuations. Okay, so the main problem over here is, okay, the main problem over here is, if you see, okay, the main problem will be uh, in batch. What happens in batch, if you're starting with n and if you're moving to n plus 1, okay, n plus 1 will always be better than n1. N, agree? I'm starting with here point, I'm moving to this point. This point will always be better than this point because I consider the complete data set, I have complete information, then I will move in the perfect direction.
Okay.
Okay, but in stochastic, what happens, because of the random nature, you cannot guarantee that n plus 1 is not equal
True.
to n, because if it is
Yeah.
here, okay, if it is moving here, then the loss is better. But if it is moving here, next random point, it is
Yeah.
worse than this one. So there is no guarantee that every time you update, you are moving towards the optimal solution. Agree? Trying to understand?
Yes. Yes. Got it.
But now the
Clear.
question is, if it is so random, then why you are using this? Surprisingly, because of this randomness only, scientists have seen that it is able to converge to this global minima faster than the batch on average. Okay, so if you see line by line, okay, if you check if n plus 1 is greater than n and if n plus 2 is greater than n plus 1, stochastic is not always moving towards a better solution. But on an average, if you see, if you give some time and just allow it to fluctuate and settle, on an average, it is going to find this global minimum sooner. That is the critical point, main point. Getting?
Got it. Got it. Yes.
Trying to understand? So, but
Yes.
with batch, what happens? If it is starting here, for example, if it is starting here, okay, so
Yeah.
there are high chances it will get settled in this, stuck in this. Okay,
True.
because every time it will see it is better than previous, but it is not having any idea that it is falling in this trap. But with stochastic, if you just allow it for some time, it will just do some random from here, from here, from here. Over a period of time, on average, it will settle, find out this global minimum faster. That is the main point of this stochastic gradient descent. Okay, so
Okay.
randomly it is taking points and then it is calculating the loss and it is updating. Okay, but on average it is able to find out, or it is able to reach the global minima, and it is able to escape the local minima in any case. Okay, so on average, stochastic gradient descent converge. Converge means what, reaching the global minima better than batch gradient. Is it clear, Karthik? Let me stop, let me know if you're having any doubts.
No, clear. But here also we are taking, for example, if we have data set having 100 rows, okay, it's calculating like 100 times. Okay. What if your data set is like 1 million, 2 millions? So again, it will calculate for 1 million. I mean, I'm talking about in terms of optimization thing.
Perfect, perfect. Excellent question, actually. Okay. But now that is actually a very good question. So the importance of stochastic lies over here. So the point is, there is one confusion usually people like face over here. So if you just think about it, I'm saying one is, okay. Let me take this. Okay, one is batch gradient descent. Okay, and over here you are having stochastic gradient descent. Okay, so if you see, the reason why we are learning stochastic gradient descent is to save time. Okay, to save time, it
Correct.
for
Correct.
faster. Okay, but for example, if you see, a very important thing you need to understand is, let's say I'm fixing epoch I'm fixing, let's say 10. Epoch is 10. Okay, so now here in over here, what it is doing. So how many times it is updating? Updation is happening only 10 times. Okay,
Correct.
rows are 100. Here also rows are 100. Okay, n equal to 100. Update happening 10 times. Okay, here update happening 10 into
100 into 10. 100.
1000 times.
1000.
Okay, so which will take more number of, so which is taking more time if you see.
Time wise, I don't updating time wise or calculating minimum error time wise. I mean, time wise.
No, no, see, here also, see, one point we need to understand if we see little closer is, in batch
Mm-hmm.
gradient, in one epoch, inside one epoch, let's say this is one epoch. Okay, inside this epoch, it is at one time only it is calculating the full loss, and
True.
it is what it is doing, it is updating the value.
Yes,
Okay,
only once.
okay, but ultimately the for every row, that means for 100 rows, loss is getting calculated or not calculating,
Correct.
but
Correct.
it is calculating at one time. Over
Yes.
here, if I call this is inside one epoch, okay, here also
Loss is
inside 100
calculating, but
rows.
in 100 times it is
uh,
calculating.
so loss, L1, L2 like that, L100, all loss
Correct.
are getting calculated, but individually it is getting calculated.
True.
Okay, so but if you're thinking about time, okay, 100 time loss is here also, 100 losses are getting calculated but at once. Here also 100
Yes.
losses are getting calculated but individually. Okay,
Yes.
so loss are getting calculated, so time is
Mhm.
consuming. Okay,
10. Yes.
okay,
Yes.
so it is consuming, but here what is happening, it is doing only uh,
One update only
yeah,
one.
correct. So it is doing only at one time, and after that it is updating only 10 times, that closes.
Yes.
Okay, but here 100 loss are getting calculated, but again for every loss it is updating. 100
Correct.
updates it's happening like that. 10 epochs, 1000 updates are happening. Okay,
Yes.
so if you see, stochastic gradient descent is taking more time.
More time, technically, yes.
Okay,
Because of 100 times new updates.
right. Okay, stochastic is taking more time. Okay, but wait, before concluding, the important point is, usually people think we are having batch gradient, we are using
Hmm.
complete full data set. Okay, and there are chances that it will get in the stuck in low, what we say, local minima. Okay, but
Yes.
even for a moment forget about local minima, there is only one minimum. But
Hmm.
even for that also, if you use batch gradient descent, okay, it need to use all data set every time, so it is taking more time. Okay, to reach the global minimum. That's the reason we bought
True.
stochastic gradient descent. Okay, it should be faster. But if you see here, for same epochs, stochastic gradient is taking more time.
Correct.
Then what is the point? But the important point is this: if you fix the number of epochs, obviously stochastic gradient descent is taking 10,000 updates. But the point is, stochastic gradient descent does not need those many updates to reach the final solution.
Got it. It might take the
Less. Okay.
starting, yeah,
Correct.
yeah, yeah.
In one epoch only, in this one epoch itself, if you are doing 100 times it is randomly taking value, that means its behavior will be like this, right? So it is starting from here. Okay, from there it went here, from there it went here, it understood it should go here, like that. In 100 updates in one epoch, or mostly in two or three epochs itself, it can understand and it can give you the best solution.
Yeah.
Okay,
But how
yeah,
many times we need to give epoch value on what basis? I mean,
that's what you
how
check
will
the
we
loss, right? Exactly. So in every, so when you actually this is better understood when you see in the
Yeah,
deep
yeah,
learning.
practical, yeah,
But
yeah.
now what happens is, when you write the code for every epoch, for every step you will print out the loss. Okay, what is the loss in this epoch? What is the loss? So if the loss is not increasing, then obviously you can stop. So batch gradient, the loss might, okay, no, constantly decreasing for 10 epochs.
Yeah.
Okay, so but in
Okay.
Stochastic, you don't need 10 epochs. Even after, let's say, 1 or 2 or 3 epochs, the loss is not decreasing anymore because it already reached the global minima. There is no more loss to decrease. So you
Okay.
can stop it over there. Initially, you will run for 10, okay, but
Mm-hmm.
it will just print for every epoch, it will print on the screen. So you can just
Same.
see after 3, there is no updates, there is no much update progress happening in epoch 4, 5. So you can stop it and then take the whatever the value you are getting at the epoch 3.
Okay. Got it.
Understood? Okay. So the
Yeah.
main point is this. So stochastic gradient descent, if you think for the fixed number of epochs, if you think yes, it is taking more time. Okay. But the
But
point
it does not
practical
need
is
those many props.
it doesn't need
Yeah.
those many epochs. So if you just okay, if you just give okay a data set and ask BGD and SGD to calculate, BGD will take so much time taking all the data set and finally it will give solution. But SGD, you know, will give you better solution in less time. Okay, but there is one more point you need to understand. But just because SGD is working better now, don't think BGD is not a solution. Okay,
Yeah.
because
Okay.
there is always see they say, right, so slow and steady wins the race. Okay,
Yeah.
even though BGD is slow, but BGD has the capacity, has the potential to give you the best result.
Okay.
Best result. The time might be more. Okay. So that's why
Okay.
in
Okay.
gradient descent, there is something called as accuracy
Mm-hmm.
versus time trade-off.
Okay.
Okay. That means what? So if you are okay to, if you are okay to have not the best accuracy, it is also best, but not the best accuracy. Okay. So, but in very fast, okay, sorry, in very less time, if you are able to get the results, okay, then you can go for stochastic. Okay, that means what? But in batch gradient descent, for example, you are having only one minima. Okay, only you are having, only there is no local minima, only one global minima. If you take batch, right? So since it is using the full data set, every time it will move towards the best possible solution, and it is going to give you the best solution.
Yeah.
Okay, but with the same thing, if you use stochastic, it might be faster, but the solution you get might not be the best because from here, if you're moving this side, okay, it might be nearby, okay, because the reason is if it is you understand, if it is here, the next time it can go here, it can go here, okay, nearby it can go, but finally it will give you a nearby solution, okay, but might not be the best result as compared to the batch gradient descent. Okay, so obviously there will be a difference. Here you are doing only one row at a time and randomly you are moving and taking a solution. But batch you are going step by step. Every time perfect all data, you are moving with all data. So it is bound to give you best result. But stochastic, it is going to give you faster result, almost the best result, but might not be the best result. If you check perfectly which one the best result you want to go, even you don't care about time. I don't care about time. Even if the system runs for 1 week also, it's fine. Then you can go for BGD. It will give you the best result. Okay. But if you say, I don't have that much time, I want faster results, then you go for SGD. Getting?
Yes, Santosh.
Okay. So, and now when we usually use stochastic is if you have large data. Okay. Usually if you have large data, right? So it takes lots of time for BGD to convert. So that's why you use stochastic gradient descent in mostly. Okay, usually also you can use for any data set, but on large data set it is explicitly preferred to use stochastic gradient descent. Okay. Mm, right, so that is one thing. And second thing is any doubts till this point?
No. No,
Okay.
Santosh.
Okay, fine. So now we are having two things. So one is batch and one is stochastic. That's fine. But we have another type also. It's called best of both worlds. That means you take the best things from both. That means the efficiency from the batch and the stochastic nature from stochastic gradient descent. Okay, batch is more efficient. Stochastic is more random in nature. That means it can converge fast. Agree? So if you take these two qualities and create a new gradient descent, that is called mini batch. Okay, that means what here in batch gradient, you're using full data set. Okay, in stochastic, only one row to update. Okay, mini batches will be in between this. In mini batch gradient descent, you will take a small batch,
Got it.
of rows to update the values.
Got
Okay,
it. Got it. Yeah.
simple. So the as I said, the only difference between these three is how many rows you are considering to update the values, to calculate
Yes.
the loss. Okay,
Yes.
mainly how many rows you are calculating to calculate the loss, and then after that you are updating the values. Okay, so
Got
over
it.
here you're using full, that's fine, but it is taking more time. Okay, I'll put this aside. It is perfect using one row, but it is, sometimes we cannot
Mhm. Yeah.
completely trust this solution because due to its randomness, right, it can sometimes go somewhere. Okay, so it's not that every time you're, because sorry, it became too clumsy. Okay, so because sometimes if it is starting here and going somewhere and coming here, okay, so sometimes, okay, so it might be doubtful. Okay, so in that case, not, I don't want like to this extreme, so I will use a mid path. Okay, so that means I'll take batch. Okay, let's say batch, you can use how many, what is a batch size? Usually let's say batch size equal to 30. Okay, that means every time take 30 rows. Okay, so if my data set is considering 300 rows, okay, and my batch size is 30, right? That means what, how many batches we have? 10 batches. Okay, so 300 by 30, right? 10 batches. Agree? So in each batch, it will update. So take in one batch, you're having 30 rows. Okay. Take these 30 rows, calculate the loss, dou L by dou M, update. Next, take another batch, update, another batch, update. Like that, 10 batches will complete. Agree? Once you complete these 10 batches, that will be one epoch. Getting or
Yes.
confused?
No. No.
Okay. So epoch is like if you complete passing in all the data set, then that will be one epoch. Okay. So, but how you are passing, it is your wish. If you're passing whole data set, that's also fine. One row, like 100 times if you're doing, that is also fine. Set of 100 or 10, 10, 30, that's also fine. But if you completed passing the whole data set one time, that is one epoch. Okay. So what is happening in batch gradient is in one epoch, it is having 10 batches based upon the data set. Okay. So 300 rows, you can, this is also parameter you can, okay, play and find out which is the best batch size. Okay, so 30, 40, take batch size, it will divide it into these many batches, and for this row, so only for these rows it will update the value. Okay, here you will get m new. With that, again take new row, update and calculate. New row, update, calculate. New row, update, calculate. Okay, that is one epoch. If you have 5 epochs, the same story will repeat 5 times. Okay,
Got it. Yeah.
so how many times it is updating? For example, if you see, uh, so yeah, so over here 10 times, right? So ten batches. Okay, in each batch, it will pass complete batch, calculate loss, and it will update. So in one batch, it is
Yeah.
updating how many times? One time.
Yes. So total 10 batches, 10 times.
Okay, 10 times. Okay, and if you complete 10 times, that is one epoch.
Hmm.
So 5 epochs, how many times?
50 times.
50 times. So now for 300 rows itself, if you consider my batch gradient will update how many times? Can you tell me?
Batch gradient,
Epoch is how many times? Epochs 5. Okay, epoch is 5. So batch gradient
5
will
times.
update how many? 5 times.
5
Perfect.
times.
So my stochastic gradient will update rows is
5
300.
into 300. 300 into 5.
Okay, 5 into 300.
Mhm.
Okay, and now coming to my mini batch gradient descent will update.
Based on number of batches,
Yeah,
basically.
you need to consider batch size equal to, let's say, 10. So it will be
50 times.
5 into
50 times.
10. So number of updates are this many. Okay, but again the same point, whether stochastic gradient, this is 1500, right? Whether stochastic SGD require this many updates? No. Okay.
Yes,
This
maybe it
is
might be
yeah,
finished in
this is
a
the
less
epoch.
number
Okay.
of epochs.
Correct.
So in
Here
the
also
same way,
50.
this is also, yeah.
Same.
Okay.
Here also 50 mini batch. But not necessarily. Even after 2 or 3 epochs also, it can give you best results. Okay. That we need to see.
Yeah.
Fine. So, but here also, if you're passing 5, usually we pass for full, but 4, this might also give. Okay. But comparingly, what happens is, if you see stochastic gradient descent will converge faster than mini batch gradient descent and
It was,
will be faster than
BJT.
batch gradient descent.
No.
Okay, converge. Okay, but efficiency wise, I mean the efficiency, the perfect
Yeah, yeah.
solution wise, batch gradient descent will be greater than mini batch gradient descent greater than stochastic. Okay, because you're using the complete data set, possible to get the best solution, small chunks, next best, stochastic. Okay, okay. But since it is so faster that usually people use stochastic only, okay, because for all practical purposes, if you use enough epochs, so it is going to give you the best results. Okay, clear?
Yes.
Any doubts?
No.
Yeah. Okay. So that is primarily regarding these types of gradients reasons. Okay. So if I try to just uh, compare batch stochastic gradient descent, I can check. Okay. Can just show you. Hmm. Okay. Yeah. As you can see, the same points. So in batch, it is using the entire data set. I mean, usually gradient descent is called as batch gradient descent, Karthik. Okay. So when they don't specify anything, it is batch gradient descent. Okay. Hello.
Yeah.
Okay. Yeah. So if it is batch size, here in batch gradient descent, the batch size is the entire data set. Okay. So, or let me just put it over here. Yeah. If you see the same thing what we have just discussed in this is yeah, this is the BGD. This is the SGD. Hmm? In BGD, entire data set we are going to use, but in here one random chosen data point. Agree?
Yes.
Convergence here it will be smooth. Okay, because it will be always towards what we say minima optimal solution, but here it will be noisy and oscillating. Okay, and
Yes.
computation efficiency less efficient for large data set. As I said, if you're having large data set, BGD is not that efficient because
Yes.
of the
It will take more time.
more time.
Yeah.
But here more efficient, especially for large data sets, stochastic.
Yeah.
Okay.
Faster.
Yeah. So and also yeah. So this also looks good. Okay. So I'll just show you this also. Yeah, over here also, if you try to understand, yeah. So this is batch, this is stochastic. So compute gradients using the whole training sample, using the single training sample. Agree? Okay. This is slow and computationally expensive, faster and less computationally expensive. Batch,
Yes.
then the
Yes.
batch. Agree?
Yes.
Not suggest for
Yes.
huge. BGD is not suggest for huge. Correct. Can be used for large.
Correct.
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 Deterministic. That means smooth in nature, but this is stochastic,
Yes.
random in nature. Agree?
Yes. Yes.
Gives optimal solution given sufficient time to converge. This is the point we are discussing.
Correct.
Okay.
Yeah. If you have time, enough time, then it will give the accurate results.
Correct. Gives good solution, not the optimal, but good. Okay.
Yes. Yes.
Perfect. No random shuffling of points are required.
True. True.
Okay. The data sample should be in random order, and this is why we want to shuffle. Okay. So this is also one point because it is randomly picking up the points. So usually you need to shuffle the data set. Okay, so that it will pick
Okay.
up randomly. Okay.
Okay. Okay.
Because if you are if there is some order okay in your data set,
Hmm.
so it
Mm-hmm.
may take the same data points. Okay. So for example, if you're having same type of data sets from 1 to 100, okay, and from
Yeah.
100 to 200 same. So it started from
Got
here,
it.
and if it is falling here again, it is the same data point. If it is falling here again, data point.
Ah,
So usually if you
got it.
shuffle, right, so every time it takes a new random point, it is completely different from the previous one. Agree?
Got it. Got it. Yeah.
That is usually we
True.
do. And see here, in batch gradient descent, it cannot escape shallow local minima.
True,
Okay,
because it will stuck with that point and it will,
correct.
yeah,
But in stochastic gradient, it can easily escape.
usually
Okay,
random because of random.
here the convergence is slow.
Mm-hmm.
Here the convergence is much faster.
Got it.
Okay, cool.
Yeah.
And I would just show you one diagram how these three look like. Okay. Yeah, this is perfect. So yeah. So over here, the how it is approached to the optimal solution. So if this is optimal solution, batch will always be moving towards the direction. Okay, every update will be towards that, as I discussed. Okay.
Yeah.
But stochastic, due to random nature, you cannot always say, so from here it can go here, again it can go down. Okay, there will be some randomness to reach the final solution.
Yeah.
Okay, but mini batch, there might also be some fluctuations, but not that much. That means if you are
Yeah.
having batch one, batch two, because of different data point, sometimes this batch might perform better than this or less than this, but there may be few fluctuations, but not as much. Okay, because we are considering more data points. Okay, we are considering 30 or 30 data points, right? So it will almost have the direction which side it should go. Okay, obviously, right, with one single point it is difficult to know which direction I should go, but with 30 I can say, okay, I'm going in perfect direction or in wrong direction. Okay,
Yes.
that's why it might be little random. Okay, so this diagram is also will help you, to just understand the whole thing what we have just discussed, what will be the nature of these three. Okay, so I hope, right, so I hope you understood these points, right? And yeah, so any doubts regarding the theory?
No, Santosh. Clear.
Okay, yeah, the main point is how many, one single line, if you think about these three, you should, what thing it should strike your mind is how many data points I am considering to calculate the loss. That's it. Okay, from that you can just track back what are the pros and cons of this. Okay, so that's about this. And if now that is theory part, but interesting point is you don't need to do anything this on your own. Okay, you already have one single library. As I said, coding is very very simple in ML. It doesn't matter at all. Okay, so what all you have learned is implemented in one single line. Okay, so earlier while OLS, right, so we saw this example, right, so where we are picking it from sklearn. Where is this? Yeah. So if you do from sklearn dot linear regression. So this will use the OLS method. You agree?
Yeah. Default by default it will take OLS.
So sklearn linear regression. So over here, it uses the, as you can see, ordinary least squares. Okay. So, but if you want to, that is one method. Okay. But now, yeah, so that is this method, ordinary least score. Okay, now we have this gradient descent, which we studied in our last two sessions. So for that, if you want to use, right, so we have something called as SGD regressor. Okay, yeah, so this is gradient descent. Okay, so the very simple. So from sklearn.linear model, you need to import SGD regressor. Okay, so
Okay.
SGD regressor, sklearn, go to this one. Okay, so this is a thing. Using this, first I will tell you. So it is very simple. So create, I hope you remember. So this is, you are importing, okay, and you are creating a class instance of this,
Yes. Yes.
and after that just fit extend y-train, done. Okay, and after that you will get the coefficient, same thing. So the don't forget the basics. So here the goal
Yes.
is same.
Just we are
So
changing
what it will give
the.
you, it will give you line. Okay,
Yes. Yes. Yes.
fine. The method is different. So we started
Correct.
with OLS, we went there, we got the line, we came back. Now we went in this gradient descent direction, we came back. But finally, we achieved what the
Specific line.
okay.
Yes.
So line is Line will have y equal to mx plus b if it is only one feature. So it will have coefficient and it will have intercept. Okay.
That,
So same thing will
that,
happen. So the code is C. What all we studied in two class is just this one line. So when you do SGD regressor, internally it uses what all things we use. Okay. So you can try this. Okay. So I hope you have this notebook. So now going back, so if you see the regressor, so this model, right? So as every model will have multiple hyperparameters, but all of these are not important. But main things are, so one is there is a loss. Yeah, one is called as penalty. Okay, this penalty is called a regularization concept, which we are going to discuss in our next class. Okay, so you can ignore this as of now. What is L1, L2? Okay, what is float? This is also related to that. Okay, and the intercept value. How many times you need to iterate? Yeah. So this is one thing you can relate. So maximum number of passes over the training data, also called as epochs. Okay, how many times you want the whole data to get passed?
yeah, maximum iterations. Okay.
By default, it will be 1,000. Okay, that is more than enough. Okay,
Okay.
1,000
Okay.
epochs, but you can just check the loss wherever it is not moving, then you can stop. And also, if you don't, okay, by default, it will be 1,000. But if you don't want it to run, you have kept it for 1,000. Okay, but this is called TOL is called as tolerance. Okay, that means if the loss is not decreasing more than this. Okay, that means in this iteration the loss is L1 and previous it is L2, but if the difference is not greater than 0.003, for example, that means there is not much progress that is happening. Agree?
True. True.
Right? Because if the loss is for every iteration, if loss is decreasing more, then we are moving towards. But if the loss is not decreasing much, if the difference is very, very less, that means we are almost staying in the same point, which indirectly means that we have reached some minima. Okay, that might be global
Yes.
minima, that might be local minima. Sometimes that might be saddle point. Okay, if you're
Yes.
not changing the loss, it's not always global minima. But obviously, you need to try with different examples, right? So you can use SGD and see if you are getting better loss than previous epochs. Okay, so yeah, you can just test with these regresses and find out whether you are stuck in any local minima or not. Okay, but usually, as I said, with SGD, you will come out of that. And if at all, if you are not seeing any loss greater than this, you can stop. That is this tolerance level. Okay. And this is all not that important. And uh, random state is like, seed. We'll give some seed value, right? If you remember, we discussed like every time if you want to repeat the this experiment, so the values the system take will be same, because if you are running random state equal to 42, if
Yes.
you
Yes.
are running my system, it will be same. Agree? Yeah. So that, and these are all not that important. Okay, cool. So this is the thing which we have actually, you know, um, studied what we are seeing. Okay, and when the main important thing over here is penalty. Okay, that will lead to our next session. Okay, so you can take this SGD regressor and you can try. Fine. So but I would say that's regarding the gradient descent. Okay, I hope you understood it well. Let me know if you're having any doubts. Okay, so in our next class you are going to see something called as regularization. Okay, because all this is fine, so we have understood that we are going to get the best solution from this above using this method. Okay, but the problem here is it should not overfit the data. Correct? If it is overfitting the data, then we will have few problems. What are that and how you can come out of that, we are going to see in next session. Okay, but I would say this concludes the gradient descent. I think we had a good discussion. Sorry, the notebooks are a little clumsy. Okay, but
Yeah.
I
No problem.
you understood the concept.
Yeah.
Right?
I have one thing.
Yeah.
Can you please go to that code?
Code. Okay.
So where we will mention here which one we need to select for either SGD or BGD or mini batch. Do we need to specify anyway?
No, if you are passing the whole data set, okay, so then that will be, if you're using the whole data set, then that will be batch gradient descent. And if you divide it into chunks and pass
Mm-hmm.
it into batch, right? So if you divide the whole data set into chunks and pass, okay, then that will automatically become the mini batch gradient descent. Okay.
So here we are not including anything as part of code,
No, 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 we are
right?
not including any part of this.
Okay. 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 Okay.
Okay. Yeah, but since you said that, okay, I'll also check on that. Actually, how we can, do just batch. Okay, but the point is, if you using whole data point, right? So that will become batch gradient descent.
That is fine. Yeah,
But here in
because
SGD regressor also, we will use the whole data point, but randomly it will pick only point. Okay. Yeah, I'll see it. I'll try to show you an example. By how you can do just BGD or SGD. Okay, but mini batches, if you divide the data and pass it right,
number of data.
yeah, that
Yeah,
will become mini batch. Okay, but I will try to find one example.
but mini batch is also, for example, we have 100 records.
Mm-hmm.
Let's say mini batch is, we divide that mini batch into 10. I mean, 10 records. Let's say each batch like 10 records. Okay, I thought directly algorithm will take 10 batches randomly. I mean, in the first batch, 1 to 10 records. Okay, let's say in the second batch, there might be 12 to 12th record. So 10 records, maybe, or one record, 19th record, 25th record, in such a way. I mean, instead of from our end,
Mm-hmm.
I mean,
Understood.
I thought like,
No, no, I
yeah.
understood. But I think usually it gets divided in sequence. If you're having 100,
Okay.
so it will divide it
Mhm.
into 10 parts,
Okay, okay, okay.
1 to
So
10.
it's our responsibility to change the data set every single time randomly instead of uh, you told me that example, right?
No, no,
1 to 100 records.
that is for stochastic. If since it is having more randomness, we need to shuffle the data. But for mini batch, that
There is
random,
no need to.
huh,
Mhm.
that randomness is not that much needed, uh,
Okay.
right? Because if you see 100 records will be different from the next 100 records.
Yeah.
Mostly, so but
Mhm.
I mean, see, in stochastic what might happen is, that's also a good question. See, for example, if you're having 1 to 100 same type of rows and 100 to 200 same type of rows, so since we are taking only one row in SGD, okay, so if that one row is initially zero point 0.1 and after that let's say it's picking 0.57, okay, so it is again
Yeah.
almost the same.
Same.
Okay.
Correct.
And again, if it is taking 99, almost the same, right? So to create some randomness, we will shuffle. But in mini batch, if you're taking batch size equal to, let's say you're having like 1,000
Mm-hmm.
records and batch size is let's say 80. So 1 to 80 will be 1 and 80 to 160 will be 1, 160 to 240 will be 1. So obviously this set is different from this set. Although there is some overlapping, okay, this 1 to 180 records is one batch 1, agree? 1 to 80. From 80 to 160, batch 2.
Yes, different.
From 280, one batch. From 80 to 160, second batch. But in 80 to 160, if you see in this 80 to 100 are similar to batch 1 because from 1 to 100
Correct.
same. Okay. So these 20 records are almost similar to this one. But that is okay because you are having remaining,
Rest of the 80
yeah,
records.
remaining
Oh,
another
60
records
records.
from another. Okay. So there is some randomness already introduced.
Yeah. Got it.
Okay.
It's a mix up already. Yeah.
Correct.
In such a way.
Okay.
Yeah, Santosh, got it. Just I thought internally, I thought before. Yeah.
Okay. Yeah. That's all. Any other doubts?
No, Santosh, it's good.
Okay, fine. So I would say that's all for today, and tomorrow let's start the regularization part. Okay.
Sure.
Thanks.
Thanks so much.